Good afternoon, everyone. My name is Jianan Li. I'm from University of Pittsburgh and Pittsburgh Quantum Institute. I'm going to talk about this current imaging of the interface ferromagnetism on the lithium molybdenate and strontium titanate. So the system we're working on is a lithium molybdenate and strontium titanate interface. This is a short overview of the interface mechanism. So the high mobility to the electron gas was found in 2004, and in 2007, people also found the signature of magnetism with this large condor effect in the low temperature. So this magnetism was measured with a talk magnetometry, and they actually found the magnetism could only be measured on the interface, but not in bulk STO material. And in 2011, the hysteresis loop was seen in even up to room temperature, and the ferromagnetic patches was imaged by this scanning squid as well. So in our group, one of the tools we use very often is MFM, as you have seen in the previous talk. Our device looks like this. So the arc shape is the interface electrode, and the circle is the top gate. So the tip is magnetized by the in-plane geometry. So once we apply a negative top gate voltage, the interface will be insulating state, and MFM can image those ferromagnetic patches after the scanning. But once we remove the voltage, those patches will disappear. So the magnetism can only be seen in the insulating regime. An interesting discovery was about the interface mechanism is the link between the oxygen vacancy and magnetism in the STO. It was discovered by the Dr. Kruger's group in Los Alamos. So basically, they reduced the bulk STO material in low oxygen pressure environment and create more oxygen vacancies in this way. So first, they found that there's additional absorption peak in the reduced material, and the peak was actually higher when the oxygen vacancy concentration was higher. And then they pumped this circularly polarized laser onto this bulk STO and found this huge MCD signal around this absorption peak of oxygen. So it actually has a pretty long lifetime, and even after the pump was turned off, it's still persistent for up to like 10,000 seconds. And this is a pattern they created with a pump laser, and after they shut the pump, they can image that with MCD signal. So those are different. Those are MCD signal with different signs they can image. So this actually give us idea of imaging them with Kerr rotation. So the Kerr the idea of Kerr is pretty straightforward. It's that all the linearly polarized lights can be decomposed into the left and right-handed circularly polarized lights. And once the surface is magnetized, the reflected light will will see this change of polarization because the two components actually reacting differently from the surface mechanism. So in our setup, we're using a high NA objective so that the light will come in different directions. And because the light in different directions is going to respond differently to the magnetic dipoles in different directions. So for example, if the dipole is in the x direction, the detector will see this difference of the intensity on the left and right. But when the dipole is in y direction, it's going to see different from the top and bottom. So by partially blocking the light on the sensor, we can select which direction of dipole we're imaging. The typical power of our laser is about 500 microwatts, and the co-rotation sensitivity of the setup is about 10 microradians per square root of hertz. And this is actually in the same order of magnitude of the theoretical limit that we calculated. So this is a test imaging. We got a piece of hard drive and actually we imaged those strips of data with our Kerr setup. So the range of data is about 2 microradians. And this is a whole setup of our Kerr imaging. So we use this balance detector to increase our signal-to-noise ratio to even higher, and we also use this photoelastic modulator. So that's going to modulate the polarization at about 100 kHz. So that's going to increase our sensitivity like tremendously. And we're actually using this 425 nanometer on purpose because we believe that there's going to be a resonance of the Kerr signal around this wavelength as MCD signal we saw in that bulk reduced STO experiment. And this is how our sample looks like. So, and we're going to compare the image of the MFM and Kerr. So this is an optical image from the FM, and we actually see those strips of ferromagnetism from the MFM scanning. And in the Kerr, we actually see something similar. Those strips are kind of in the same direction, and the range of the data is about 600 microradians. So one of the future plan is to do this time-resolved Kerr imaging, and the laser we're using is pulse laser, so we can do pump and probe experiments. And we know that the LAO to the electron gas can respond up to gigahertz microwave frequencies. So the idea is to send this gigahertz pulses to the top gate of LAO, so the interface ferromagnetism will be tuned by these gigahertz pulses. And in this way, we can, by controlling the phase difference between the pulses of the laser and the gigahertz microwave, we can actually see the time evolution of the Kerr images. So we can try this in different temperatures and even in external field or using a laser pump. So in summary, we are working on this electrically tunable ferromagnetism on the LAO interface, and the magnetic signal is actually in resonance with the oxygen vacancy absorption wavelength. So our setup is able to image the LAO interface magnetism with a Kerr rotation, and we're going to do the pump probe experiment with electrically pumping. So in this way, we might be able to see the time evolution of the interface ferromagnetism. So if you are interested in our system, we have more talks in the following days. So thank you for your attention.